I'm just going to give you a little bit of background about Titan and about how we study Titan, and then I'll get into more detail about why it's so interesting. So Titan is really a unique body in our solar system. You can see, I think most of you recognize Saturn in this lovely image that was taken by the Cassini spacecraft. But Titan is hiding down here. So it's not very large compared to Saturn. It was discovered by Cassini Huygens in 1655, so we've known about it for quite a while. As I said, it's the largest moon of Saturn, with a diameter of about 5150 kilometers. That also makes it the second largest moon in our solar system. It's just slightly smaller than Ganymede. Although that does make it also bigger than Mercury, so this is not an insubstantial body, even though it seems so small compared to Saturn. The mass is about 0.0225 Earth masses, and taken with the diameter that I just mentioned, that means that has a density of about 2 grams per centimeter cubed, 1.9. And that means that it's about half rock and half water ice. We also know that the surface temperature is about 94 Kelvin, so it is very, very cold on Titan. And most importantly, and the reason why I study Titan, why I think it's so interesting, and why I'm talking about it today, is that it's the only moon in our solar system that has a substantial atmosphere. There's one other thing that's really important about Titan that's really critical to everything I'm going to be talking about today. And that's where Titan sits on a methane phase diagram. So Titan's atmosphere is composed mostly of molecular nitrogen, just like our own atmosphere, but the second most abundant constituent in its atmosphere is methane, CH4. And so this is a phase diagram for methane. The temperature is on the x-axis, pressure is on the y-axis, and if you remember these from when you were in school, over here in this area of pressure and temperature, methane would be a solid. Up here it would be liquid, and down here it would be a gas. This looks fairly similar to the phase diagram for water. And much like Earth is very close to what we call the triple point for water, so this point right here where you can have solid, liquid, and gas all coexist together, Titan is very close to the triple point for methane. And so that means that there are a lot of really interesting processes that can be occurring because we can have methane in these different phases, very similar to the way that water is close to the triple point and the way that water behaves. I said that it's the only moon with a significant atmosphere. Triton has a little bit of an atmosphere, Io has a little bit of an atmosphere, but Titan's atmosphere is very dense. The surface pressure is about 1.5 bar, so that's about 1.5 times the surface pressure here on Earth. Again, it's a molecular nitrogen atmosphere, about 98%, and so that actually means that it's also, not only is it the only moon that has a substantial atmosphere, but it's the only other dense atmosphere in our solar system besides our own that is mostly molecular nitrogen. And so that's actually one of the reasons why we find Titan so interesting, because we think that Titan in some ways is kind of a frozen analog of Earth before there was life on Earth, before Earth produced all of this molecular oxygen that we have in the atmosphere now. One of the things that happens in Titan's atmosphere, though, is something called photochemistry. So we have photons that are coming from the sun. We also have energetic particles that are coming from the magnetosphere around Saturn. These photons and energetic particles come crashing into the methane, into the nitrogen. They break them apart, and the pieces that they make are very reactive. And so they're running around in the atmosphere, reacting with each other, building more and more complex molecules, things like hydrocarbons and nitriles, which are just organic molecules that contain carbon or carbon and nitrogen. The subsequent chemistry between these molecules that get built from this photochemistry results in the formation of Titan's really characteristic haze layer. So you can see it in the picture that was on my title slide. You can also see it pretty well in this picture, this kind of global haze layer. You can see it actually has some structure. This is something we call the detached haze layer. Doesn't show up very well on the projector, but this funny little blob right here, we've actually watched form in real time over the last couple of years. That's a pretty substantial sized vortex at Titan's south pole that is, we think, now made out of hydrogen cyanide ice. So Titan is a nice place to send a spacecraft. You probably don't want to visit there yourself. Aside from the nitrogen and methane, though, there are a couple of other molecules that are potentially kind of interesting. So there are also oxygen-bearing molecules in Titan's atmosphere. There have been 3 that have been detected to date. Carbon monoxide, carbon dioxide, and water. That goes in order of decreasing abundance. So CO is the most abundant. It has an abundance of about 50 parts per million. So that's not very much, but that actually makes CO the 4th most abundant molecule in Titan's atmosphere. And So one of the reasons why we care about these oxygen-containing molecules is that the building blocks of life on Earth, so the small molecules that all of life on Earth is based out of, things like amino acids and nucleobases, are made out of a very small number of the possible atoms on the periodic table. So carbon, nitrogen, hydrogen, and oxygen are 4 of the most important atoms for building these molecules that we consider to be the building blocks of life. And Titan's atmosphere has all 4 of these types of atoms in its atmosphere, but it also has an atmosphere that is very favorable for organic chemistry to occur. And so Titan's kind of unique in the solar system because it has this, what we call reducing atmosphere. So it has an atmosphere that doesn't have a lot of oxygen in it, which is very favorable for haze formation, for organic chemistry. But there is some oxygen, so there's the possibility for some really interesting chemistry to be occurring. And that's one of the reasons why we think Titan is so interesting and why we're trying to study it. So how did we start to study Titan's atmosphere? So Titan's atmosphere, there's debate about when Titan's atmosphere was actually discovered. So there was a drawing that was made in 1907 that showed some evidence of limb darkening, and the observer suggested that this potentially meant that Titan has an atmosphere. There was a lot of debate about whether or not the telescope was good enough for him to actually have been able to tell that, or if it was just kind of a figment of his imagination, or what was going on with that. But about 30 years later, 40 years later, some spectra were actually taken of Titan by Gerard Kuiper that showed very obviously the significance of methane. And so then it was clear that Titan did indeed have an atmosphere. One of the things that I love about this paper that Kuiper wrote is it's just called Titan, a satellite with an atmosphere. And I kind of felt like there's supposed to be like a question mark or an exclamation point or something at the end of that title that's just like, that's weird. When you read the paper, it's very striking because he had observed all the giant planets, and he had observed the Galilean satellites and Titan. And if you just look at the spectra without knowing which ones are which, Titan looks very much like Jupiter, very much more like Jupiter and Saturn than it looks like Europa and Io and Callisto and Ganymede, because it does have this atmosphere and have this methane signature. And that was how he knew immediately that something was going on. So we knew about the atmosphere since 1944 for sure, maybe 1907, depending on how you think about it. And we knew that there was methane in the atmosphere, definitely since 1944. And so already we thought this is probably going to be a pretty interesting place. In the early 80s, the Voyager spacecraft, on their grand tour of the solar system, flew through the Saturn system. And they returned this amazing or disappointing or frustrating or beautiful image of Titan, depending on how you look at it. Scientists in general, planetary scientists really specifically, don't like it when they can't see things, and we could not see the surface. So there could have been small or large titanians running around, jumping up and down and waving at the spacecraft, and we would have had no idea because we couldn't see the surface. Luckily, Voyager was carrying an infrared spectrometer called IRIS, and so we did get more data than just this frustrating hazy orange ball. And so this is the infrared spectrum that was taken of Titan. And you can see that the things are labeled with all kinds of chemical formulas. So there's things like, this is hydrogen cyanide, HCN, acetylene. If you would like to barbecue on Titan, there is plenty of propane. There's also ethane, all these different organic molecules. And so now we knew that there wasn't just methane, but there was also this very rich organic chemistry occurring in Titan's atmosphere. And so this, of course, then is even more frustrating, because now we can't see the surface, but we know that there's organics in the atmosphere. And so, of course, we're very much in a hurry. We need to go back to Titan as soon as we possibly can. As soon as we possibly can has a different definition for NASA than it has for the rest of us. And so it took us a little while. But we're now able to explore the Saturn system with a spacecraft called Cassini Huygens. This is a joint NASA-ESA mission. ESA is the European Space Agency. It launched in 1997, 16, 17 years after the Voyager encounter. It arrived at Saturn 7 long years later in 2004. Cassini is carrying the Huygens probe, which is shown here. So this is the heat shield of the Huygens probe. And the Huygens probe descended through Titan's atmosphere down onto its surface on January 14th, 2005. Huygens carried 6 instruments to the surface, and I'll show you some of the data from Huygens, I think. Cassini carries 12 instruments, 11 of which are still operational today. So Cassini's now been in orbit around Saturn for 11 years, and will continue until the fall of 2017. You should definitely stay tuned. It's going to be an amazing final 2 years. Cassini is already in the process of changing her orbit a little bit, going into something that we are going to call the proximal orbits, which is a very, very boring way of saying that the engineers are finally letting us get reckless with the spacecraft. And we're going to start taking Cassini between the rings in Saturn, which is not something we've been allowed to do before, because it is pretty dangerous to the spacecraft because of the possibility of running into icy ring particles at very high speeds. But once it's on that trajectory, it's going to crash into Saturn no matter what. So we don't care if we hurt it or lose contact with it at that point. So it's going to be a really interesting couple of years. We're going to learn a lot more about the rings that we've been able to learn. In the very last few orbits, we will actually be in Saturn's atmosphere, trying to take direct measurements of Saturn's atmosphere. And then Cassini will try to send data back all the way down, much like Galileo did at the end of Galileo's mission. So although that's going to be a hard day in 2017 to get out of bed, we're very, very excited for the science that we're going to get at the end of this mission. So definitely stay tuned for that. One of the other things that has been really great about Cassini and really great about having a mission at Saturn for 11 years is just to give you a sense of seasons and what a year is like. So a Saturn year, and therefore a Titan year, is about 29.5 Earth years. So to get any kind of understanding of seasonal change, you need to be there for a long time. And one of the things that happened, because we have a different definition of let's get there as fast as we can compared to NASA's definition, is that we actually arrived in the Saturn system at about the same time that Voyager had been there. So that was really nice to be able to confirm some of the observations that Voyager had made. So summer solstice is in May 2017. We're going to get past there. So we've already gone through basically the whole spring. We're in summer now, and so we've been able to learn a lot about seasonal changes. And one of the main seasonal changes, actually, that we think is in fact a thing that happens annually, is this formation of this giant vortex at the South Pole. We think that alternates forming at the winter pole, and is probably the precursor to what will eventually become what we call a polar hood, so an area that's basically encased in a giant cloud for most of the winter. So because of our experience with Voyager, because of the knowledge that we have gained about Titan and about the Saturn system from Voyager and from ground-based observations, the cameras on Cassini were designed very differently than the cameras that were carried by Voyager. And so the camera on Cassini has some very specific narrow wavelength filters within methane bands and outside of methane bands to try to be able to understand Titan's surface and also the processes going on in its atmosphere a little bit better. So we do have the ability with the camera to be able to see down to the surface, which is not something that we could do with Voyager. Although there are much better instruments for actually studying the surface on the spacecraft than the camera. One of the things that we've been doing a lot of, and it's what I actually do kind of as my day job, is trying to understand this thick haze that kind of engulfs Titan. And from the spacecraft, we've been able to learn a lot more about it. We've been able to study the structure. You can see here that it has a lot of detailed structure. If you've seen the images of Pluto, its incredible haze, Pluto's haze also has very similar structure to it. And so this is really a fantastic time actually to be studying haze in planetary atmospheres, because we have this new hazy place that we had no information about before, and it'll be a really good test for a lot of the things that a lot of the explanations we have come up with for Titan. We think the haze is primarily composed of all of these organic chemistry words, if any of you ever took organic chemistry. So things like hydrocarbons, which are molecules made of carbon and hydrogen, nitriles, which are things that have a C triple bonded to an N, amines, which are a nitrogen that has some hydrogen on it, and then aromatics are things like benzene, these ring structures, which are also really interesting. The other thing that we've done some work with trying to study the atmosphere is trying to understand clouds and also some of the haze that we see. There's also rain. We have evidence of rainfall occurring on Titan. Again, I mentioned at the very beginning that Titan is very close to the methane triple point. And this leads us to talk a lot about methane's hydrological cycle. And so we have methane cycling between the surface and the atmosphere in a very similar way to the way that water cycles between the surface and the atmosphere here on Earth. And so sometimes we have these giant clouds appear. That's what you're seeing in this image, is a big cloud towards the South Pole. We have evidence from the spacecraft that if we see one of these giant clouds and are able to look at the surface afterwards, the surface has appeared to darken, which we take to be evidence of rain. The clouds in the rain are primarily composed of methane, although sometimes we also see clouds that are made out of ethane instead, which is C2H6. So that's one of the primary products of this photochemistry that I was talking about before, so it's quite abundant. Of course, I mentioned we have our special filters, so we can see down to the surface now. We're not stuck with our fuzzy orange ball. And not only that, we've actually been to the surface now. So these are Culls, which is a size classification. So they're about 10 centimeters across. These ones that are that look very, very large are actually just like right up against the camera almost, which is why they look so large. So not only are they cobbles, but they're rounded cobbles. So immediately when this image was returned to Earth, everybody got very excited. The interpretation now is that the Huygens probe landed in maybe a dried stream bed or some kind of wash area, so somewhere where there is very clearly transport happening by fluid. And that leads to erosion and processes that act to round these cobbles. Now, the thing is that there's no rock, the way that we think of rock, no silicate rock on the surface of Titan. Titan's bedrock, Titan's surface is actually made out of water ice. And so we think that these cobbles are actually made out of water ice, or maybe some combination of water ice and organic molecules. And so that's kind of going to be one of the themes of everything that I show you and talk about today, which is that the physical processes happening on Titan are very familiar to us, but the chemistry that they involve is very, very different. So that's the image from the Huygens landing site. We think that the bedrock is water ice. There's possibility for some other things like ammonia maybe. Also there's a lot of organics on the surface, as I'll show you in a second. We think that this kind of material is pretty typical of the areas that are white. So Titan has kind of the light stuff and the dark stuff, and which is a very technical scientific term, but that's really how we talk about it most of the time. One of the other things that Cassini has discovered, now this is not coming from a camera, this is coming from the radar that's carried by Cassini. So when you're looking at radar data, things that are very dark are smooth at the wavelength of the radar. So Cassini's radar is 2.2 centimeters, so things that look very dark are smooth at the scale of about 2.2 centimeters. Things that are bright or brighter are more rough at that scale. So if you look at this image, ignoring the fact that it is from a radar and not a camera, you kind of immediately will recognize what is going on here. These are large lakes and seas. The one on the left is Kraken Mare, which has a diameter of about 1,000 kilometers. Over here is Ligeia Mare, which is about pretty similar size. So these are very large bodies of standing liquid on Titan. They're mostly methane, although there's also some ethane and some of these other molecules I was mentioning before, hydrogen cyanide and propane and all of these different things. You can also see that there's all these really interesting channels. There's some little lakes around here. And we actually see, I don't think I have a good picture in here. We'll find out. But there's actually a pretty extensive system of lakes and seas and channels at the North Pole. So going back to this idea of the dark and the bright, if you are looking at the North Pole and you see something dark, it's almost certainly a lake. I'll show you in a second what the dark stuff is if it's not the North Pole. The lakes are super interesting to us for a lot of reasons, and one of the reasons is that we have all this organic chemistry going on in the atmosphere. A lot of that material eventually ends up on the surface. And once it's on the surface, it can be transported around by different kinds of processes, by liquid processes, by processes involving wind. But a lot of these processes will act to concentrate it and collect it in these basins where these lakes and seas are. And so a lot of this material gets mixed into the methane and ethane. And so there's a possibility for a lot of really interesting subsequent chemistry that can occur. We already have this really interesting chemistry happening in the atmosphere, but now we can have even more happen on the surface. So things that are soluble in methane and ethane will dissolve, and then possibly have subsequent reactions. But things that are insoluble will either end up kind of precipitating out onto the bed of the lake or sea, where they might be in contact with water ice, or they could end up as some kind of goopy whatever sitting on the surface of the lake. We don't really know that yet, and so there's a lot of lab work that's kind of in progress right now, trying to figure out exactly what happens when all of this stuff ends up in the lakes. But there's a lot of possibilities for some really interesting chemistry. If you are looking at the equator, we'll go back for a second. If you were looking at any of this, everything that is dark in this picture, just so that you understand the scale of what I'm about to say, everything that is dark in this picture are extensive dune fields. Similar in scale to what we see on Earth, similar in spacing and height, all these different things, especially to the dune field in the Namib Desert, Africa. But again, we don't have silicate rock on the surface. These dune particles, these sand-sized particles, are composed of some combination of organic materials. We still don't really understand how they form, but the data from the dune fields is not consistent with water ice. They're certainly not water ice sand particles, and they're not rock. So that kind of leaves us only with organics as our last resort. One other place that is really interesting for us on Titan, although we don't see very many examples of them, which again is another kind of similarity between Titan and Pluto, are impact craters. So this is one of the few impact craters that has been identified on Titan. This crater is called Selk. It's about 90 kilometers in diameter, and this is about 1,000 kilometers northwest of the Huygens landing site, which was approximately equatorial. So one of the reasons that we think impact craters are really interesting is because there's no liquid water on Titan, right? It's 94 Kelvin. Water is ice, and not only is it ice, it's ice that is so hard it essentially behaves like granite. And so all of a sudden having liquid water is super interesting because, again, there's a possibility for more chemistry that could be happening. This might also happen if we have cryovolcanoes, maybe similar to those on Enceladus or Triton. We've certainly not seen a cryovolcano erupting during the mission. It's up for debate whether or not we see evidence of them on the surface or not. But regardless, if you have an impact crater, the top will freeze over very quickly, right? It's 94 Kelvin, it's very cold. And it will freeze over very quickly. But in doing that, it actually acts to insulate the water below. And so we can end up with a crater lake, frozen solid at the surface, but with liquid water below that can persist for many tens of thousands of years. And that'll give us a lot of time to do chemistry. And so these organic molecules, which have pretty much never seen a water molecule in their life, and they've certainly never seen a liquid water molecule in their life, are going to react actually quite quickly. They're going to do something called hydrolyze, and they're going to form things like alcohols, acids, maybe the amino acids, the building blocks of protein on Earth. And so there's also a lot of really interesting chemistry that might occur in these types of places. So the title of the talk had the word prebiotic in it, and that word means a lot of different things to a lot of different people. So what is the prospect for life on Titan, and what are we looking for? And that kind of depends on where we look. And in this way, Titan is very different than any other object in the solar system. So one of the taglines that people have been using in terms of explaining why we think Titan is so interesting is life's origins, life today. And so we think that there's the possibility of being able to study both of these things on Titan. And it's going to depend on where you look. So the lakes are very interesting to us. We think that one of the requirements for life is a liquid. We're pretty sure that liquid water is good for life, seeing how life on Earth is based on it. But we don't know if liquid water is the only liquid that life could use. And so that's one of the reasons why the lakes on Titan are so interesting. We have a liquid, we have a lot of building blocks of life, and so this is a good test for us to try to understand if life can exist using other liquids. One of the things that's really great about going to the lakes to try to answer questions about whether or not there's extant life in our solar system is that if we go to Mars, which is fairly similar to Earth, liquid water a little bit now, much more in its past, the crust is made out of silicate, rock the way that you think about rock. If we find life on Mars, there's a pretty good chance that it's going to be pretty similar to life on Earth. And that's going to cause us a lot of headaches, because then we're going to spend a really long time trying to figure out if we accidentally brought it with us, or if it is actually Martian life that originated on its own that has nothing to do with us. And of course, it would be very exciting to find life on Mars, don't get me wrong. But if we find life in Titan's lakes, it will not have been contamination on this spacecraft, period, end of discussion. Earth life will not live in Titan's lakes. It just won't. It's too cold, there's no water, it's just not gonna happen. And so this is a really good, good test for us as well, because we won't be trying to figure out if it was contamination or not. On the other hand, we have no idea how to look for it, because it's going to be life as we don't know it, and that's very difficult to look for unless there's some kind of squids or krakens or something swimming around that are very large and very obviously saying, hello, we're alive, which would be lovely. I would really like it if they would make it that easy on us. I suspect they won't. So the lakes are really interesting for testing this question about whether or not you need a liquid, and if any old liquid will do. The other thing that I have not yet even mentioned about Titan, because Titan is so darn interesting, we often forget to tell this to people, is that there is an ocean beneath Titan's crust, a liquid water ocean, much like Europa and Ganymede and Callisto, potentially Pluto. I don't know about that one yet. And so this is another place where we can actually test this idea that if there is liquid water somewhere, that there may also be life there. So we think that if there is liquid water, there's the possibility that it's in contact with rock. If it's in contact with rock, that also means that there could be hydrothermal events. Everywhere you find a hydrothermal event on Earth, you find life. Even in the most absurd conditions you can imagine for biology, there's all kinds of life at these hydrothermal events. And so that's another place that we could go to look. We would expect that that life might actually be much more similar to life on Earth. Than life that would exist in the lakes. And so there's these two different environments where there could potentially be life today, and they would test two very different questions that we have about how life originates and where it can evolve. But one of the other reasons that Titan is really interesting, which has nothing to do with whether or not there is life on Titan today, is that there's also this very interesting chemistry happening in its atmosphere. And as I mentioned at the beginning, we think that Titan is kind of a frozen analog of Earth before there was life on Earth. And so this is a place where we can go to try to study the processes that may lead to the origin of life. We can't build a time machine, at least not yet. And so we can't go back in time and try to figure out what was going on in Earth's atmosphere before life originated, but we can build a spacecraft. And so that's one of the other reasons why we think Titan is so interesting. Yeah, there are people like myself who do atmosphere simulation experiments. We produce analogs, or the best analogs we can, to the haze particles that are in Titan's atmosphere. And there are some people who have been working to take that material and then mix it in with various different metals or minerals, clay minerals, different kinds of silicates, those kinds of things, put in water, put in different things, and just see what happens. And thus far, I mean, this is really something that people have only started doing in the last year or so I haven't seen much come out of it yet. But that is definitely something that people are thinking about. Not necessarily for Titan, although anything that we find out will definitely tell us things about Titan, but more because of this idea that it's an analog to the early Earth. We think the core is solid. And in fact, Titan, this is one of the surprises from Cassini. So Titan and Ganymede are about the same size, right? I think I've said that now like 5 times. And Ganymede has a magnetic field, which is weird, because most of the small things in the solar system don't have a magnetic field. We think that you need a liquid core for a magnetic field, and so presumably Ganymede has a liquid core. Ganymede is then fully differentiated, right? It melted to the point where everything completely separated based on density. All of the most dense stuff is on the inside, all of the most dense stuff is on the outside. It's exactly the same way that Earth is. We thought that Titan would be the same way, based on the fact that it's about the same size as Ganymede, And that turns out to not be the case. So Titan is not fully differentiated. It did not melt so much that everything completely separated by density. And so it's kind of an intermediate case. It's partially differentiated. So there definitely is, as you can see, although this doesn't do a great job of showing you, but there is definitely a structure. We do see some kind of core. There's certainly evidence of a liquid water ocean and a crust. But the stuff in the middle is kind of smushy. So we think that this area in particular is probably a mixture of rock and water ice. And that tells us that it didn't fully differentiate because otherwise those materials would have separated. So because of that, we think that there wasn't enough heating to potentially really ever have that much liquid in the core. We don't see any evidence of a magnetic field. Now we can't get as close to Titan as we can get to a lot of the other moons with the spacecraft because of the atmosphere. And so it's a little bit harder to try to figure out if Titan has a magnetic field or not, compared to flying by Enceladus or something like that where we can get very close. But there isn't any evidence at this point to suggest that Titan has a magnetic field, which makes sense given the fact that we now know that it's also not fully differentiated. The lakes are in this little box right here. And so they're all confined to this fairly small region of longitude, which is weird. You don't generally see any kind of behavior with longitude on a planet. And so we don't understand why that region is the only place that has all these lakes and seas. Now there are smaller lakes up here. These are informally called the cookie cutter lakes because it really looks like someone was just running around with a cookie cutter, cutting all these little holes in the Titan. We think, although the idea had been rejected at first, it's been revived lately that these might actually be karst, the lakes that are formed by dissolution. We see these all over the place on Earth. But again, completely different chemistry on Earth. This limestone that's being dissolved by water that forms these lakes. Here we think that there are organics dissolving maybe organics, because they don't really dissolve water ice very well. We don't really understand that either. But this just gives you a sense even of the difference and the different kinds of lakes that we have at the North Pole. When we looked at measurements of the gases in the atmosphere, you could actually tell that there was a vortex in the North Pole, around the North Pole, that was basically behaving like a dynamical wall. And so it was enriching a lot of molecules, things we could detect at the North Pole we couldn't detect at the South Pole. That was when we got there. We've now been there for 11 years. We've watched as the North Polar hood has dissipated, this dynamical wall has disappeared, the abundances of the molecules are now very similar to what they were at the equator, the temperatures have changed. And a few years ago, all of a sudden there was this giant cloud at the South Pole that has increased in extent a little bit. We now see evidence of not only just this vortex from the cloud, but also now looking at the gas phase measurements, we're seeing again this effect of a dynamical wall, but now at the South Pole, we're starting to be able to detect molecules at the South Pole that we can't see at the North Pole. And so we've actually watched the circulation change now over the mission, which is one of the things that's really amazing about a mission like Cassini, is having that long baseline to be able to watch all these things happen. The models are actually not doing a great job of reproducing the behavior that we're seeing. They were super excited and already like, oh yeah, we're going to see these great things happen. And they happened kind of the way that the models had predicted, but on a super different time scale from what the models had predicted. And so people are still trying to understand that. But we've definitely seen a lot of effects of season, even in things like the clouds. When we got there were clouds at the South Pole all the time. And then we had quite a number of years where we didn't see clouds ever. And we keep thinking that clouds should appear at the North Pole any day now. And we've seen some little wispy clouds appear every once in a while, but if we're right in our understanding of how Titan's atmosphere works, at some point very soon we're due for a gigantic storm at the North Pole. So if that doesn't happen by the end of the mission, I don't know what we're going to do. It's going to be very frustrating. But yeah, so we see a lot of these seasonal effects. So any kind of pre-existing topography from impact craters or from whatever other processes may have been occurring either currently or in the past, the liquid is obviously going to take advantage of that. And so, it's pretty easy to envision how all of this erosion happens once you have pebbles and cobbles and things that can be transported by the liquid. If we could only figure out how to make those in the first place, everything would be better. We see things like, we see mountains. There's certainly evidence of some level of tectonic activity in the past. We don't really think that it's ongoing at this point, but there are mountains that are about 1 kilometer tall. You know, again, similar, I feel like a broken record lately, but you know, we see mountains on Pluto now. And so, you know, probably the mountains are actually fairly similar in terms of composition to the mountains on Pluto. So again, those will also be really helpful for trying to understand how these processes are happening, but we still don't know a lot of things about how all of this stuff happens. Right around the time of Voyager, as soon as they saw this organic chemistry happening in the atmosphere, people sat down and they put together some models of the chemistry occurring in the atmosphere. If you run the chemistry as we think that it's occurring now, based on now not just Voyager measurements, but also Cassini, if you run these models for 4.5 billion years, age of the solar system, there should be many kilometers globally of ethane liquid on the surface. There's very clearly not. So there's this very wonderful paper written by someone on my thesis committee in the early 80s, something about Titan's global ocean. So there's a prediction that in fact the entire moon would just be covered in liquid. That's very obviously not the case. And we knew that actually before Cassini from some measurements that were done on Earth, that there weren't, you know, at least there wasn't a global ocean. So we have a lot of questions which are going to, I think, probably remain from the mission. And one of them is why, you know, where is all the ethane? In terms of evidence of, you know, maybe a past global ocean or past, you know, very large bodies of water, we don't, or liquid, methane, whatever that liquid is, we don't seem to have much evidence of that. The surface is getting constantly covered by organic material raining out from the atmosphere. And so it doesn't actually take very long to erase features on the surface. We have fluvial erosion, we have wind transporting all this material, you know, forming these large dune fields, and so it's unclear if there was a large ocean in the past, if we would even be able to see evidence of a basin like that at this point in time. One thing that we do see some evidence of, though, I kept saying, you know, there's lakes in the North Pole, there's lakes in the North Pole, lakes in the North Pole. What about the South Pole? There's one lake in the southern hemisphere called Ontario Locus. It's actually the first lake that we found on Titan, and it's very disappointing. It doesn't have any of this super interesting dendritic structure. It doesn't, you know, it's not very big. It's very boring looking. And everyone's kind of like, that's it. That's all we get. Luckily, we got the other stuff too. But we see some evidence in the southern hemisphere of ancient lake beds. So there are structures that look like at some point they had liquid in them, but they don't right now. And so one of the things that we think may happen, I don't know if people have heard of them or not, but there's something that called the Milankovitch cycle on Earth, which is to do with things like precession and the way that the orbital elements of Earth evolve over time. And so you end up with these long-scale cyclic variations. We think that actually happens on Titan too. And so over a time scale of something like 200,000 years, it's predicted that the lakes basically flip hemisphere. And so for 200,000 years, they would all be at the North Pole, and then they would switch and they would all be at the South Pole, and they would switch back. And so we don't necessarily expect that over the southern winter that these lakes would fill back up again. We think they've been empty for quite a long time at this point. So we know what the vast majority of the surface looks like for some value of looks like. Between the camera, the visible infrared mapping spectrometer, which is what this image is from, and the radar, we've seen the entire surface. It just depends at what resolution and with which instrument. And so, for example, the radar is by far our best tool for understanding what the surface looks like. And so we have pretty good coverage with radar of the entire surface, but the resolution, it just really depends. The Cassini website, which I think is saturn.jpl.nasa.gov, is updated very regularly. They put press releases and new information and stuff there all the time. The other place to go is the Cassini imaging website. So the Cassini images are released within 24 hours of hitting the ground. So you can go see the pictures if whenever the most recent flyby was, which was sometime last week. If there were images taken from that flyby, they're already down on the ground and publicly available. You could Google Cassini ISS, which is the Imaging Science Subsystem. The website is cyclops.org, but that's a cool place just to go see like what has the camera been looking at. And of course, you know, it's not a Titan orbiter, it's a Saturn orbiter, and so there'll also be amazing pictures of Enceladus and Rhea and Dione and the rings and Saturn and all these other cool things. And they do, even though they put the raw and processed images there, they also have like a little blog where they occasionally write little blurbs about whatever it is that they just imaged. And so that's kind of a fun thing just to keep up with what the mission is up to also. But just the Cassini website is really good.